Hello and welcome to Operations with Power Series. Honestly, these notes are pretty guided. I really almost feel like you could sort of figure this stuff out by yourself, but nonetheless, as a person committed to your education, here I am. All right, so Power Series. All right, they're of the form that you see here. Let me grab my highlighter. Come on, highlighter. Here we go. Right, so this is a Power Series. Right? It's, the sum from, n equals 0 to infinity, some number given by an times x minus c to the n. All right? So these power series, right, really, when you throw the x in there, just like a series that is not in terms of x, right? A series that is strictly in terms of n approximates a number, right? A series that is in terms of x will, pretty much approximate a function. So guess what? Things that we can do to functions, we can do to power series, such as differentiate them, integrate them. And the good news is it works exactly the way you want. Don't you love that? All right, so let's do this. All right, so here's a series. All right, and it just generates a polynomial, right? I'm on number 1 right now. So let's just expand this by listing out a bunch of terms. All right, so in this case, we're going to have f of x equals, all right, so when n equals 0, I'm going to get a0 times, x minus c to the 0, that's just going to be 1. Plus, all right, now let's let n equal 1. a1 times x minus c to the 1, okay, plus a2 times x minus c squared, and so on and so forth until we get to our nth term. All right, so now moving on to number 2. Oh, it's a polynomial. Let's differentiate it, right? That is totally a thing that we can do. All right, so if I just from the polynomial, okay, right, this is just power rule. So f prime, a0, that's just a number, so that goes away. So then we move on to the next term, all right, our term for when n equals 1. Oh, okay, well, the derivative of, I'm right here now, a1 times x minus c, that's just going to be a1. Okay, now if we differentiate our next term, the a2 is just a scalar multiple, right? But then we do power rule on the x minus c part, right? So the 2 will come down in front. So 2 times a2, and then this becomes an x minus c to the 1, right? And so on and so forth. I probably should have listed out a few more terms, but all right. Ultimately, we're just going to keep bringing down the exponent in front as a coefficient and knocking the exponent down by 1. That's power rule, right? So for our nth term, right, the differentiation will be, n times an x minus c to the n minus 1. That's it. All right. So we have a polynomial that is very easily represented as a series. Okay, so let's see if we can find the series representation for f prime of x, right? And I think that I have hinted in the past that usually if you can find an expression for the nth term, right? It's like that's pretty much what you're going to throw into your series. All right, so let's do that, right? But I've also given you a hint that you're going to need to check something. So, let's get it down first. All right, so in this case, f prime of x, all right, is going to be, right, the sum, all right, and this, right, an times x minus c to the n minus 1. Fantastic. Now, the only thing we need to check is the index. In other words, we're starting at n equals what? our function f started at n equals 0, but we do get a little bit of weirdness here if n equals 0. Not too much, I would say, but I think, right, I mean, we don't even have really a 0th term. It's just the 0th term would just be 0. So let's just start at n equals 1, right? That's really the first thing that we see here, right? So we'll start at n equals 1. All right. So really, all right, and we go through the process, right? But if you're actually working with a given power series, you don't want to have to list out all the terms, right? Especially if the thing's a hot mess, right? But we very quickly realize that power rule within the expression inside the series, it works, right? So, for example, all right, if we have the derivative, so in other words, the derivative with respect to x of some power series, so, some coefficient x minus c to the n, that's our power series, right? You just apply power rule to the stuff inside and you check your index. All right, so in general, I would say it's probably going to be, from n equals 1 to infinity, right? But it's just power rule. Bring your exponent down, multiply it by everybody else, knock the degree of your exponent down by 1, right? Couldn't be easier. And in fact, that is exactly what I want to write in this little gray box here. Okay. All right. So we've had the setup, right? That here, our function f is given by this power series. All right. So then its derivative is given by, and we'll call this f prime. I'm a big fan of writing things lots of times. The more we write them, the more we know them. And so then let's just, also make a note here. I'm just going to say, check your index. Why is this not writing? Let me just pair the pencil with my iPad again. All right, and let's see if they will talk. So the note that I am going to be making is check your index. There we go. Right, but in the bubble, we're just going to put It's power rule, right? It's just power rule. And it's really only ever going to be power rule because it's a power series. It's a series of powers. So power rule is really the only thing that's going to apply. You're not going to have to use like weird differentiation rules here because it's a power series. Power rule is pretty much the only thing that's ever going to apply. It doesn't get much simpler than that. All right. Yeah, so that's differentiation, and you can do this for second derivatives, third derivatives, et cetera, et cetera. You just got to check your index. All right. On to integration. Okay, so let's take the same power series, and we'll expand it again, but I think you kind of see where this is going. But you know what? Let's do it. We want to believe it. All right. So let's do an expansion. All right, for f of x. All right, so again, we'll have a0 plus a1 x minus c, right? And then the term when n is equal to 2. All right, I will do my third term. I think I learned my lesson last time. And so on and so forth. Okay, so let's integrate. All right, and don't forget your plus c, right? Again, it's a function, right? Everything still needs to be in order, right? If for a function you would put a plus c, for a series, we're going to put a plus c. All right, so let's find the antiderivative of f of x. So, all right, when we integrate a0, all right, we're going to get a0 and an x, right? We're basically just going to be integrating each term. Right? Now, each of these is going to be basically like reverse power rule, right? Luckily, there's no like chain rule to compensate for, so we don't need to worry about a u sub or anything like that. All right, so this is going to be, you're going to have a1 times x minus c, but that gets bumped up a degree, and then over 2, right? a2 x minus c now cubed over 3, right? And you get the idea. So that ultimately, right, you're going to have, it, right, an stays the coefficient, right? And then x minus c to the n plus 1 all over n plus 1. All right. Oh, and I forgot my plus c. There it is. Look at me. But I caught it. All right, so find a series representation for the polynomial that we created. All right, so this is going to be easier if we sort of put our plus c in front. All right, so I'm just going to go over here. I'm going to quickly erase my plus c from here. And then let's see if I can do this. All right, so I'm basically going to scoot this guy. How do I, come here. Can I, here. Am I able to circle this? Oh, that copied it, so that's fun. That was not what I needed. Where's like my cut and paste tool here? All right, maybe I'll just erase it. Sorry. Okay, so I'll put that back in, right? That's just a0x, but I'll put my plus c in front, right? And you see why that's maybe helpful, right? Because c is really our degree 0 term, so it's nice to have it in front. Okay, so let's try to write this now with its series representation. Okay, so, all right, well, we're going to have a series. All right, obviously, reverse power rule applies, right? This thing right here, that's our nth term, right? That's our general expression. All right, so that's what's going to get thrown in our series. Okay, so we're going to have an x minus c to the n plus 1 over n plus 1. All right, but let's check our index. All right, basically when we have n equal 0, we still want to be generating, right, a0 times x, right? So in other words, right, this corresponds, all right, with n equals 0. So that still needs to be the case. And then you're like, oh man, what about the c? Where does that go? Well, don't worry, we will take care of that. All right. So we're still going to start with n equals 0. I know, feels weird, right? Maybe. And now this series will generate all the little terms of our polynomial, right? But it's not going to generate the c for us, right? There's really no value of n that we can plug in. I mean, we could plug in -1 to get like an x to the 0 term, but then you've also got a 0 in the denominator, and that's no good, right? So right now the series will generate all of the terms of our polynomial, but not the plus c. So guess what? We have to add it in. All right, and I would like that to be in blue. All right, so I am going to put it in front. Why? Because if I put it here, it looks like it's part of the series, even though it's not really. If you wanted it to be contained in that series, you would need the whole thing in parentheses, but this is ambiguous. It's just not great notation. All right, so, all right, we put the plus c in front to basically just, make it clear that it really is the terms of this series plus a constant, right? Which is why it's kind of helpful here to write it in front. You're less likely to forget about it, in my opinion. Okay? All right, so, all right, I'm going to spare you for number 8. I think you kind of get the idea. So let's cut to the chase. So if we've got a power series, of this format, such and such, then its antiderivative is given by, right? So again, I keep writing in green. All right, so the antiderivative is given by, right? And it's sort of one of those things where it's like, if a series is defined for n equals 0, its antiderivative will be 2. Sort of, just like how if a function is defined at x equals 0, its antiderivative will be 2. So here, we're good on our index. So an will still be the same. An is just a number, right? But you're going to be operating on, the exponent. Okay? All right, and so this is right. It's just reverse power rule. That's it. All right? How much easier could it be? So of course, right, this is a very easy idea to work with. And so we should expect that, there are going to be a few little nitty-gritty complications, although honestly, it's not that complicated. Because here's the good part, all right? If you've generated a new series by differentiating or integrating, guess what? The radius of convergence is going to be the same. However, right, notice I said the radius of convergence, not the interval of convergence, right? That exact interval, meaning we have talked about what's going on the end points, right? That may be different, okay? So the exact interval of convergence might differ. Okay, so let's see how this plays out. And this is a series that, right here, we worked with, I think in the previous notes packet, talking about interval of convergence, right? So, let's see. All right, so for f of x equals x to the n over n, I'm pretty sure, right? So let's just write all this out so that we have it. All right, and you can look back at your previous notes from 9-8, right? In this case, your radius of convergence was 1, and then our interval of convergence, right, since we were centered at 0, right, 1 in either direction from 0 becomes -1, and 1, and I mean, you would certainly go through all these steps, but we don't need to do that right now. We have already done them, and we figured out that when x equals 1, that generates a harmonic series which diverges, but when x is -1, it is an alternating harmonic series which actually converges. So that's your interval of convergence for the function itself. So now let's get f prime, okay? And then we'll talk about its interval of convergence. So we're differentiating. So we're going to be aware of the fact that we're going to have to check our index, okay? But let's apply power rule. So that's going to be n comes down, we knock the degree, all right, off our exponent, right? And all of that is over n, and so that actually simplifies, right? That's going to simplify to just x to the n minus 1. So now let's check our index, right? If we start at n equals 0, it is no longer a power function, right? It's a rational function. So it must be the case that we need to start, well, let's see, when we start with n equals 1, let's see, does that work? Yes. And so here's a way to check, right? Because, I told you check your index, but guess what? It's not the case that you're always going to be adjusting it. So here's maybe the way that I would think about it, all right? So when n equals 1 here, all right, so let's look at this, all right? When n equals 1 in our original series, what is the term that we generate? Well, we get x to the 1 over 1. So we get x. So if the n equals 1 term in our original function gives us x, the n equals 1 term in our derivative should give us the derivative of x. It should give us 1. Does that happen here? Well, yeah, when n equals 1, we get x to the 1 minus 1, x to the 0, that's 1. So we're good. So basically, when n equals 1, right, for our derivative, we get the derivative of the n equals 1 term in the function. So our derivatives are aligned, all right, for the appropriate n value. So that's a nice way to check, all right? Right, when in doubt, just check. So you won't always be changing your index, but you do got to look alive. Normally, you would just be changing it for domain issues, but just always check, all right? So our interval of convergence, it's still going to be from -1 to 1, but we've got to recheck our endpoints like entirely, okay? So let's check. Let's check when x equals +1, right? I'm learning, always check the +1 first because, well, we know. All right, so when x equals +1, that's going to be a +1, all right, to the n minus 1. Okay, so that is just 1 plus 1 plus 1 plus, that diverges pretty clearly. Okay, so +1 does not come to the convergence party. Usually if a function, right, if your original function did not include a number, your derivative probably won't include that number too. So I think from the get-go, we were pretty confident that this was going to continue to, like, it's not going to all of a sudden be defined where the function wasn't. All right, really we need to check on the bracket. All right, but why not? Let's go through it. All right, so let's check x equals -1. All right, so when we do that, -1 to infinity. All right, so that's going to give us -1 to the n minus 1, which is going to be, let's see, -1 to the 0. So 1, -1, +1, -1, plus da-da-da. Oh, that diverges too. Okay. All right. So guess what? -1 now does not come to the convergence party for f prime. Okay. So let's check on the antiderivative. All right. And yep, notability is or explain everything's being weird. Let me see if I can try to move all this at once. Why are you being weird? Explain everything. Come on. Everybody move. Okay. All right. Well, that's good enough for me. All right. So now let's check the antiderivative. Okay. So again, we're going to do, I'm just going to do a C+. That's the, not your grade. That's your constant of integration. Just as soon as you're doing an integral, just put it there. You will totally forget it. All right. So, all right, I'm going to use reverse power rule on this, right? So we're going to have, all right, x to the n plus 1, right? It's already over n, right? But then we also have to put it over n plus 1. All right, so now let's think about our index. Okay, so when n equals 1, are we getting, all right, so let's sort of make a hypothesis here. All right, let's test n equals 1. We know that when n equals 1, in our original function, we generate the term x. So it should be the case that when n equals 1 in our series, here in our antiderivative, when n equals 1, we should generate the antiderivative of x. We should be getting x squared over 2. So let's check that. We get x squared over 1 times 2. Good. Okay, so our index is good. Fantastic. All right. Cool. All right, so now we just need to test our endpoints, right? The radius of convergence, it's still going to be, or I'm sorry, we're still going to go from -1 to 1. We just need to test individual endpoints. Oh, why is this being so weird? Oh, boy. Okay, all right, well, I'm just going to do my best because it just randomly decides it doesn't want to move things the right way. Okay, so let's test we are testing x equal to +1. Okay, so when x equals +1, we have c plus the series. Oh, yeah, 1, oops, right, 1 to the n plus 1 over n to the n plus 1. Well, guess what? I'm just going to sort of scoot this over here. All right, that's the same thing. That is the worst sigma I ever attempted to make. All right, guess what this is? I mean, well, 1 to the anything is just 1, and this is 1 over n squared plus n. All right, and this, if I had this space, I would do this more formally, but this very closely resembles a p-series, right? It's not quite a p-series, so I might do a direct comparison test here and find that it converges. Don't worry about the plus c, because if the series here converges, adding a plus c, right, that's another finite number, like a finite number plus a finite number, that is still totally convergent. So the plus c is never going to change anything. But this converges by direct comparison test with p-series. So guess what? Now +1. You have come to the convergence party. All right. And there's a good chance that because -1 was included in our original interval of convergence for f of x, right, that, -1 will be included in our antiderivatives interval of convergence. So let's see, that becomes -1 to the n plus 1. And so here is when I would use absolute convergence, right? This is basically just the alternating version of the exact series that we just generated, right? So if the all positive version converges, then so does the alternating one. So guess what? Everybody comes to the convergence party. Fantastic. Yay. All right, so we've got a couple examples on the last page, and really this is it. It's not too bad. A little bit of, again, little bit of detail work, but that's what you guys do well. All right, so let's do this now with something a little less obvious, perhaps. All right, it's still a power function. All right, because all of, this stuff here is just going to be a number when you plug in a value for n, so it's still like some number times x minus 5 to the n. All right, so totally a power series. All right, so find the intervals of convergence for all of these things. All right, well, first we have to find the interval of convergence for the regular function itself. So ratio test. All right, and if we're taking, we're going to take the absolute value. We'll do it. And really, we're going to do the n plus 1 term. So that's going to be x minus 5 to the n plus 1 over n plus 1 times 5 to the n plus 1. I know, it's awful, right? Divided by, so times the reciprocal of all of this business. Really, I'm leaving the alternating part in because really we should show why we drop the negative part, right? It's because it's in an absolute value, so here we are. All right, so this will sort of collapse. All right, I'll drop all my negative stuff because it is absolute value. I'm going to put all of my x minus 5 terms in one place. And all of my other stuff, we'll say, in another. And then let's start to see how this might simplify. Okay, so the first fraction, right, that just means we have one more x minus 5 on top than we do on bottom. So we will have an x minus 5 up here. Good, and that, right, takes care of this first fraction here. Now, when I look at the 5s, I have a 5 to the n over a 5 to the n plus 1. So I have one more 5 on bottom than I do on top, and that's sort of taken care of all that. All right, and then not really I can do much in terms of canceling, right, but we will very easily be able to take that limit, right? As n goes to infinity, this piece will go to 1. So I am just left with the limit as n goes to infinity of x minus 5 over 5, which is just itself, you know, it's not determined by n. Okay, and so in order for our series to converge, we want that common ratio to be less than 1. All right, and so now again, we need to sort of remember the things from the last lesson where we say, oh, okay, well, that's going to be the absolute value of x minus 5 over 5 is less than 1, right? So then that really means x minus 5 is less than 5, okay? So this means, right, that it could be the case that x minus 5 is less than 5, or x minus 5 is greater than negative 5. So that leaves us with x is less than 10, or x is greater than 0, right? You know, centered at 5 with a radius of 5, 0 to 10. All right, so now in terms of our interval of convergence, we know it's going to be from 0 to 10. We just have to check the endpoints. So let's check x equals 0. This will be fun. All right, so when x equals 0, all right, in our original function, all right, let's see what that generates. So we have from n equals 1 to infinity, negative 1 to the n, negative 5 to the n, over n times 5 to the n. Okay, and then if we simplify that, right, really it's almost like the two negatives make a positive, right? So this piece right here really becomes like a negative 1 to the n times negative 1 to the n times 5 to the n. And this becomes a positive 1 to the n. So that kind of drops out. So we're left with, right, the series from n equals 1 to infinity, 5 to the n over n 5 to the n. This should look familiar, because when we cancel some stuff out, we're going to get 1 over n. That's the harmonic series. It diverges. Okay? You know, and you should say, you know, diverges by harmonic series. So 0 does not come to the convergence party. Okay? So now let's check x equal to 10. When x is 10, we'll get negative 1 to the n, and then 10 minus 5 will be a positive 5 to the n. And look what this simplifies to. Right? These will cancel, and you'll end up with the alternating harmonic series, which we know converges. So 10, you may come to the convergence party. Hooray! All right, let's now work with f prime. Let's go get it. All right, so f prime of x, we're just going to do power rule. All right, so I know this is a hot mess. So guess what? The -1 to the n plus 1, nothing is going to change about that, right? That's just a coefficient here. All right, but we will need to bring the exponent, all right, down in front, right? The -1 to the n plus 1, it just determines the sign, and differentiating does not change the sign, right? It's the power rule that will change the sign, if the sign changes at all. All right, so then it's n times x minus 5 to the n minus 1 over n times 5 to the n. All right, again, these are all just, no, you're just doing power rule on the power part. The rest of these are just numbers. I know you feel like you want to do like this whole big quotient rule, right? But all of this is with respect to x, not with respect to n. If we were differentiating with respect to n, this would be horrible. But because it's with respect to x, it is tolerable, albeit a little clunky perhaps. So this is going to be -1 to the n plus 1. Your n's will cancel, and you'll have x minus 5 to the n minus 1 over 5 to the n. And of course, we are going to want to check our index. I sort of just by default wrote n equals 1, but let's just check and make sure that this works. So in our original series, the n equals 1 term, all right, let's see. All right, generated, right, the n equals 1 term, it generated our linear term. So right now, when n equals 1, do we generate a scalar term, a constant term? We do. So I think that we are okay. All right. So now, all right, we know that the interval of convergence, right, it's going to be from 0 to 10. It's just a question of filling in brackets versus parentheses. All right, I'm going to let you do that because I am running out of room. So please finish that up and we'll compare notes when I return. All right, I'm going to help you with getting the antiderivative here. All right, but then I will leave you to check the interval of convergence because really that was the last lesson, am I right? All right, so let's integrate. Oh dear, I forgot my plus c. Let's add that back in there. Okay, so plus c. And then, all right, so now we basically just need to do reverse power rule on this series up here. Again, so the alternating part is not affected. It just determines the sign, right? Okay, so then let's see. We've got x minus 5 to the n plus 1 now. Over n plus 1, but times the other stuff that was also down there, right? We can't forget about it. All right. So this is kind of a giant mess, but that's okay. All right, because we've got lots of things that we can do for a giant mess. I mean, there's really not a whole lot that I can do right now to clean this up. Again, the interval of convergence will be from 0 to 10. You have to decide on the endpoints, and a lot of this will clean up very nicely when you plug in 0 for x and 10 for x, just like before. So it's not going to be too terrible. Okay? All right. And then I want to leave example 3 for you guys because I want you to remember what is a differential equation and what would we do, right, to show that this power series, this function given by a power series, is a solution to that differential equation. All right, so hopefully you have a little bit of time left in class after this. Discuss, all right, and then come back ready with a proposed solution, all right, for example 3. Good work.